Hello, Professor. This is a video of my final project. So this particular file, file underscore project.zip, is a zip file that I'm going to start off with. And I'm going to do all the installation as well, just to make it simpler, clearer. So going in, extracting, and we have the file underscore project right here. So I'm just going to go into open a new command line tab. And this is just this particular problem is just on my personal computer. It doesn't come with the project. So this particular directory, first source um, virtual n slash bin slash activate. This activates the virtual environment, and um, pip install -r requirements.txt installs all the text requirements, and all that needs to be done now is do flask run. And this is going to take a couple of minutes. In the meantime, I'm just going to start running the client. This directory is where the client is within um, um, the directory of the project. And once you get here, sorry, have to activate the virtual env again, go into the, the client. And then once inside the client, just do npm start. Actually, sorry, I have to redo that. Just npm start again. Um, please just make sure that the server is running before going into the client and npm run starting the client. Um, so just type Y because there's a um, port collision here. And once this is done, this page opens up. Um, and this page by default, it indexes the text files, which are essentially right here within benchmark sets. And once that's done, we can now use the test files to actually run a test command. Now just run python test.py. Sorry, I have to activate the once again, and then just do python test.py. What this does essentially is that it uses all the queries and tries to run the queries to the Python uh, test files, which is essentially the time data set that I'm using. And once it runs through each and every one of those um, document, each and every one of those queries, and compares them with the respective relevant documents that are right here. Um, all it does is give the mean average precision of the test run, and we'll see that in a second right here. Sorry for the delay. This is a figure of the mean average precision over the 82 documents. This is a figure of the recall, the final recall of each of the documents, or for each of the queries across all the documents. And this is a frequency distribution of the average precision values, just to see how how they're distributed across different documents and different frequencies, and how many 100% precisions there are and how many lower percentage precisions there are. The same for recall as well. All this is in the report. And this is just a scatter plot associated with the query lengths and average query precision of each of the queries. And most of them seem to be having an average query precision of like mostly more than 50%, especially most of the queries with relevant documents that are more than about 5 to 8 documents in this range. This is also very detailed in the report, and the same goes for recall. And finally, as you can see right here, I have a overall mean average precision of about 55% right here. Median is about 55% as well, and then the recall, most of the median of the recall is 1, and mode of precisions essentially this just shows that most of the precisions are 100%, and there are about 18 queries that have 100% precision. And again, same thing goes for mode of recall, which is again 1, which just shows that most of the queries were able to retrieve the relevant documents um, at some point or the other, or at some ranking or the other, once they were returned. Um, so there's that. And going back to the actual project, this is the final project. This is the final result of the project. And index web pages, essentially what it does is when we click on it, it makes a request to the backend, makes a request to the server, and this is still pending right now. So once the indexing takes place, go to the once the indexing does take place, it starts from right here. So it starts from right here, run processing, which is in run. I'm going to run processing is right here. This takes in type websites, goes to the crawler, crawls the websites, and keeps indexing them right here. The words, the mapper gets like a list of all the tokens and their frequencies within that document. Reducer puts them um, in their respective um, objects. And when I say objects, right, I'm using multiple different objects: token info, token occurrence, and document reference. Token info essentially contains IDF and occurrence list. Token occurrence contains document references and the total count of that word in that particular document. And document references contains the link to that particular file or to that particular web page, and the length of that web page with reference to the number of words that are in it, or the relevant number of words that are in it that have been indexed. And that's what the crawler does. It indexes them, and once this all this data is indexed, right, it's essentially taken back to run processor, and after all this process happens, the inverted index and the total number of documents are detected, and they're returned, and the IDF is calculated, and the document vector length is calculated, just like in the implementation notes. So if you go here, there's both the formulas for the IDF calculator and the document vector length right here. Um, there's that. So there's that. And the next process, or the next thing in the process, is saving the inverted index in a SQLite 3 local database within the Python documents itself. So right here, I'm establishing a connection to the SQLite database, and then I'm inserting everything. All this insertion is essentially taking place in a database called invertedindexes.db, and then um, all the initially all the values in the indexes table, which is the table in which we're inserting into, are deleted just to make sure that there's no repetition or anything. So that's why we're running that. And once that's done, um, all the different occurrences are inserted into sorry, all the different occurrences are essentially inserted into the indexes um, um, table. So the one thing to notice about this here is token occurrences is saved just as a string that contains all the values. As a string, a list of all the different. Let me just show you. So this just contains this, the link, then the length of the document, and the number of occurrences of that term. For example, in this case, climate, and the number of occurrences is, let's see, about 491 in this specific document. And that's what it stores it as a string. I just thought that was the best way that I could store it. And that is that so far. And I think the indexing process is done on the front end. So going back here, we can just search for, let's say, climate change here. And all that we need to do now is say submit, and we get all the list of documents in ranked order. We could just go to one of them. This is an actual web page that was crawled. This is one of the seed web pages. So we can go to a more relevant one with an actual article about climate change. And there we go. That's one of the most relevant ones about climate change. Um, yeah, so there's that. And the code for that, again, is starting from here. So this is where the request is gotten. The query is, in this particular case climate change, and then it's fed into load underscore inverted index function, which is part of the run function again. And once you go in there, you'll see the load inverted index, taking the query and converting into a map, retrieving the relevant rows from the database or the local database, and then making sure that the token occurrences are segmented and put in lists right here. And then this is sent to the cosine similarity calculation function or file. So cosine similarity calculation is right here. In this particular document, just goes to the cosine similarity into the retrieval algorithm, and this is where all the weights for each of the query terms are set, and the document score relevant scores are calculated, or the document scores are calculated in this particular case, along with the document lengths which are retrieved for each of the relevant documents that actually contain any of the terms in the query. And this is the array which is returned for it, document scores with document length. And the length of the query is calculated right here, a normalized length for the query. And this is the algorithm for it. And after this, all these values are fed into document ranking, which just takes and here I'm just taking the implementation nodes algorithm to calculate the document ranking. So essentially, the normalized document ranking in this particular case. So the document length is y, and the document scores are s. S over y times length of query should give the normalized document score, and they're all sorted in decreasing order right here and returned. And once this is returned, we just go back to run.py, and the rankings are returned. This extract links only file just extracts the links, and this is being used again in, I'm sorry, I just need to rename this file to um, app.py for purposes of running Flask itself. And then once we get here, we're extracting the links from each of the ranked documents and JSONifying them and sending them. And we're obviously receiving them on the front end right here and populating all the code right here. Specifically, the React code for that is right here. And this is just populating the list right here, and app.js. This contains the buttons for indexing and also let's see, um, the search field, which essentially is it contains a text area with the submit button, which is essentially all this right here. And these are the final rank documents, which can be scrolled through like this. And yeah, that's my final project, Professor. Thank you.